All right, let's start. First of all, does the sound coming okay? Can everyone hear me?
Yeah, I can
Yeah.
hear you.
Appreciate it. Thank you. All right, so welcome to Math 477. My name is Triad. I'll be your instructor for the summer course. So I guess before we even start lecture zero, which is about the class structure, just a few things about, the online environment. The first thing is, as you already noted, I don't like to sit in front of, the camera. I like to walk around or, kind of move around when I lecture. So kind of make it easy. So, right, I mean, I'll keep the camera on so that, I'm here. But no one has to open their camera or anything like that. So, and if you find my walking around distracting, let me know. I might turn off the camera, but probably, right, keep the camera on is better. Okay, so that's about the camera. In terms of interaction, right? As I move around, I don't, look at the screen too much. I won't see your chat, okay, on time. So this is probably something you want to note, and I will remind everyone again and again every lecture. If you want to interact with me during the lecture, right, get my response, speak into the microphone, okay? I think folks are more shy and would like to kind of private message me for some reason. If you want to do that, it's better to send me an email, okay, after class or something, and I'll respond to you. But if you want a live response during class, uh, just speak into the microphone, all right? Chat may or may not be responded to during the entire lecture, not because I want to ignore you, just because I may not even look at the screen, okay? So that's that. Okay, any questions so far? All right. Oh, sorry. One more thing, right? In terms of these things, it's an online environment, so technicalities, technical issues might happen. Like I'm the sound when I come through, or I might share a content. I might appear to be talking or something, while I'm not sharing the content with you, or things like that, right? So if you note anything that's kind of weird, again, catch me right away. Speak in the microphone. Say, hey, I think you're not sharing, the homework problems or something, right? So that I can correct the issues right away. Okay. Yeah. So anything about quality control, quality issues, and things like that, tell me right away. All right. So now let's move on to lecture zero, which is really about the class structure. Okay. So yep, 477, right? My name, my email address. So like I said, right, anything sort of, I don't know, private, personal, whatever you want to ask, don't private message me on the chat during lectures. Send me an email. All right, I'll respond. Pretty on time. So otherwise, like kind of like course materials, things like that. Please just speak into the microphone. All right. So class structure. So the first thing to note about this class, right, or about the online class, and I have to say this again and again, this is a Rutgers thing or maybe a math department thing, I don't know. But the class, even though online, is online synchronous, okay? I'm aware that these days, a lot of online courses, like Coursera and stuff, right, are online asynchronous, meaning you can just, do the lectures whenever you want, the recordings are there, you take the exams sort of like at a flexible time, right? Not here, okay? Not this class. By rule, okay? Not even what I want, but just by rule, by the math department, everything happens during class time, okay? Like lectures, like exams, okay? So you have to dedicate, okay, this block of time for the next 8 weeks for the class. You're expected to do so, okay? No excuse involved, like you have a trip to Hawaii planned, etc., etc. Those are not accepted, right? Think of it like you attend an in-person class, except that it's conducted online for some reason. Okay, so very important, synchronous. So yep, 2 items you want to pay attention to, right? The attendance quiz, which we'll explain, and participation quiz, right? And we'll explain more about that, and right, the recordings. So the classes will be, the lectures will be recorded, but right, again, it's not meant to substitute for live lecture. So it'll only be, I'll share with you, right? But it will be shared only after the homework of that lecture is due. As you see, right, we'll talk about this. We'll solve, the class is built around, problem solving and things like that. So the solutions to the homework problems will be done during class. For that reason, right, I don't want to show it to you right away. It will be shown, right, it will be shared after, right, the homework is due. Again, right, just encouraging or, yeah, making you to attend class. All right, so very important about prerequisite. So these days, I think calculus seems to be not very well focused on kind of skill set. Well, whatever that is, right? But for this course, not all, right, the entire material, but when we move on to continuous random variable, okay, sort of like the second half of the course or so, calculus techniques will be required. I say this again and again because, I have taught this course many times and students always trip up when it comes to the calculus part, especially when it comes to techniques of integration, integration by parts, just simple integration or, double integrals and things like that. I am not teaching you these things, right? I mean, you come into this class expected to be able to perform these calculations. If you can't, well, basically, right, the homework and the exams will involve this, and it might reflect on your performance. Okay, so keep that in mind. All right. Well, I guess, even though Calc 3, right, Calc 2 and Calc 1 are assumed because, right, those are prerequisites to Calc 3. All right. Exams, 2 midterms, 1 final. The exams dates have been given. And again, right, the exams are during class time. The midterms are during class time. The final, you should expect it also to be closely aligned with class time, all right? Except that the final exams are supposed to be 3 hours. So, there's some sort of like a little bit 1 hour before, 1 hour after, or something like that. When we get the time, I'll let you know, right? But you are expected to be available, right? To be proctored, on via, responders, right? With webcam available during the class time at the exam dates, right? Which is already posted on Canvas. So the midterms at least will be 80 minutes. So on those dates, we won't have the full lecture. Basically, the remaining of the time, we can give it to office hours or review, depending on how, how best to proceed. So when it comes close to those times, I'll let you know. But basically, right, you have to be available, right, during those times. So another feature of my class, at least, is I don't give any practice exam. If, right, you have to have practice exams, you can't live without it, you can't, do well without it, my class is not for you, okay? That's it. I don't do practice exams. Like I said, my class is built very strongly around problems, working on problems. Well, because, I think theory alone won't, be enough. So we will do homework problems during class. You will see those homework problems assigned, of course. And, right, the exams will be drawn from the homework. And so you can see that as your practice exam, if you will. But basically, right, it's very traditional. If you understand the homework, you master the homework thoroughly, you will do okay, maybe well on the exam. If you don't, you will not do well on the exam, period, okay? So I guess another follow-up question is like, okay, how will the exam problems be similar to the homework? I mean, I try to make the exams exactly like the homework problems. The system has been abused, meaning, right, because it is exactly like the homework problems, students find a way to access, the solutions while they're taking the exam. I don't want to make that happen. So you will not see exactly, okay, the homework problems on the exam. There will be modifications. But on the other hand, right, I mean, I guess you'll see that the problems we do in this class are quite challenging. So to kind of strike some kind of balance between the two, I'll say maybe 50%, right, of the problems will be drawn exactly from the homework. The other 50 will be modifications. I won't tell you which, right? I mean, your task is to master the homework thoroughly, understand them thoroughly, right? And if it's exactly like the homework, you still have to do it from memory. If it's not like the homework, then you have to use your understanding to see how you modify, right? The homework answers to the exam answers, okay? But yeah, so that's how the homework and the exams are related to how my exams are structured. Again, when it comes to grade, I don't do curve. I don't promise a curve. Most of my classes don't have a curve. So if you, right, I mean, whoever, right, want to have an easy time, right, summer classes, get your credit, move on to a different course, or get your degree and get out of Rutgers or wherever. Maybe, right, my class is not for you. All right. Like I said, I think my class is very straightforward. If you work hard, emphasis work hard, okay, and study all the problems, you should be fine. But if you want an easy time, my class is not designed around that, okay? So in fact, right, I mean, go on Rate My Professors and read all, the negative review about me, right? They're all true. I'm not accommodating, okay? Meaning that you get what you get out of your performance. Your personal circumstances will not be considered when I assign grades. All right, this applies to everyone. The reason is if I consider someone's special circumstance, I have to consider all, right, special circumstances, and that cannot be done. So, right, again, I mean, like I said, right, everyone struggles these days. Everyone wants to get out of school fast and start, make a living, things like that. I completely understand that point of view. However, right, I cannot design a course to support that. That's all, right? So the course is very objective. You get what you deserve, okay? And if you find that, not working for you, please strongly consider, right? No, nothing wrong with that, okay? So I just want to warn you ahead of time that that's how the class is structured as far as grades concerned. All right. Any questions so far? Okay. So, this is introduction to probability, right? So you can call it like the first course in series probability theory, if you will. The way I want to do my course, right, in general, is that I want to show you how the problems are done. And the reason I believe in that is because, right, it will give you an extra, right, chance to practice these problems, right, besides solving the homework problems yourself, and then, right, see that on the exam. So basically, you get to see at least the problems twice, right? And so basically the course is built around that, meaning that if you don't understand my homework, you cannot do the homework, you don't care about the homework, I don't think you will do well on the exam. But we will solve the homework problems during class time, right? So kind of focus more on the problems, a little bit lighter on the theory, okay? Meaning that we will still, of course, discuss the theory enough, but we'll discuss it enough so that we'll move on to the problems to see how the theories are used, right? But so, yeah. What else? Yeah. There are two Canvas sites, right? One is like the main Canvas sites where you have the attendance quizzes, the persuasion quizzes, the exams, right? And the other one is designated for homework submission only. The reason is because the grade is not supposed to access your other information. So we have to, have a separate Canvas site, right, for homework submission. Yep. So you will see you will have the solution file, right, posted after each homework's due. But before that, I'll show you the solution during class time, but it won't be shared with you, okay? Until the homework's due. All right. Yeah, right. So the theory will be provided through the lecture slides, and the homework problems will be provided through it's not really a slides, but problem PDF files, right? Kind of like slides, not exactly. So lecture slides will be freely shared with you, right? You will see exactly this slide, these slides, and the next lecture right, slide posted on Canvas after class, but the problem slides won't, right? The problem slides involve the solutions, so they will be posted after the homework's due. Okay. So, well, maybe, right? So the way when we come to like these problems is that I'll give you, some time, right, to read the homeworks, to read the problems first, right, and to get an idea what the problem's about. We might not give it 3 to 5 minutes, probably that's too long, but I'll give you some time, or I'll ask for like some input, right, on what you think the solution to to these problems might be. Be strongly warned that these problems are not designed to be solved within 3 to 5 minutes. Okay, in fact, you may not be able to solve them even if you think about it in 1 hour. Okay, and that's fine. I mean, these problems are not meant to be trivial, but you will be guided, right, through these problems. You'll be provided solutions for them. So, but still, right, it's better for you to kind of like interact with the problems, get some input, right, during the problem session. So to make the class less boring, right, and also, kind of strengthen your understanding from that point of view. So we'll kind of give time, right, for each of the problem a little bit. I mean, depending on how the pacing goes. Yeah, so these are the problems. Each lecture, right, will have 10-minute attendance quiz, a preparation quiz, right? You already see that today's quiz is posted, right? So middle of lecture means for us 6:55, right, to 7:05. How would the lecture questions, how will the quiz questions will be given? They will be drawn exclusively from the materials, right, between the quizzes, right? So for example, today's quiz will be on whatever we talked about up to that quiz today, right? Well, in fact, for the first 2 quizzes, meaning today and Wednesday, they will not be graded based on precision. If you submit something, you get full credit. The reason is I think we're still within add drop deadline, and I don't want to, kind of make people retake the quiz and things like that. But the quiz will be graded based on precision starting on Friday, okay? The reason is, again, so the quiz won't be proctored, right? You can access any materials you want while doing the quiz, and basically the solution is being provided for you, right? So it's only meant for you to kind of follow the lecture up to that point, know what the question's about, and then write down the solution, so to speak, right? So again, enforcing the idea you have to be in class, right, to follow a lecture to do these quizzes, all right? But it's also meant to be a break, right, in between. If you finish the quiz early, submit on Canvas. By the way, right, the deadline for submission is 10 minutes, right, within the quiz. So 7:05 is the absolute deadline, right? I will not accept any late quizzes because, again, you might be sleeping somewhere, copy the solution from your friend, and then submit, right? That won't be accepted, okay? So 10 minutes, strictly enforced. But if you do it, you finish early, we'll take a break, and then we'll be back at 7:05, right, for the remainder of the lecture. Okay. Any questions so far about these things? All right. So like I said, any questions you have, feel free to let me know, either during lecture or send me an email. I just want to check to see if the class ends at 7:55 or at 8 o'clock. Give me a moment. $7:55. Okay, cool. All right. So any question? If there's no question, let us begin with the first lecture. All right. So, sorry, maybe one more thing. Textbook, right? So textbook, I want to say this, that textbook is not crucial for the course in this way, okay? That basically, there is a official department textbook for the course by Gallagher, I think. And there's this more classical textbook from Ross that basically I follow when preparing my slides, right? The materials are basically the same ish, right? It's just the contents are swapped around here and there. So as far as we're concerned, right, all materials will be provided to you through the lecture slides, which is the theory, and the problems, the homework problems, solutions, right, which is the practice where you have to master that for the exams. So you're the type of students who really want to read, right, above and beyond the class materials, great, feel free, right? Get either of those textbooks and read them. But I want to say that, right, my class is designed so that, right, you should focus on the class materials first, which means the lecture slides and, right, the problems set. If you have any questions about those things, right, please clarify with me about those materials first. Because I had some students, for some reason, who just don't want to look at the slides, who go straight to the textbook for some reason, read the textbook, and then say that, right, the textbook doesn't make sense, or at least the materials don't make sense to them. Well, again, right, if you want to read a textbook and ignore the lectures, that's your style, that's fine. But my class is not designed around that way of studying either, okay? Because if you want to read the textbook, then there's no reason to go to class, I think. So once again, right, I mean, the lectures are designed to be self-contained, meaning that everything you need to know is from the lecture slides and from problem sets. And I'm very happy to clarify any questions you have about those contents, okay? Textbook, you feel free to read on your own, but especially in the summer context, I strongly doubt that you have time to properly digest the textbook, okay? But it's up to you. All right, so now having gotten that out of the way, right, let's start with, I guess, the first basic building block of probability, okay? I guess, well, so maybe let's start out with maybe a simple question, right? What is probability? I'm not sure if that's even a meaningful question for a lot of you. But right, I guess you kind of throw the word probability around a lot, right? Especially these days with machine learning, AI, and whatnot, right? But what is probability, right? So when you think about probability as some sort of like conversational thing, right? It's not just a probability as a word. It should be probability of, right? The probability of rolling a six, right? When you throw a dice, the probability of tossing two heads when you roll the coin twice, things like that. So it's probability of something. Okay. So it's that about that something that we want to focus on first. So that something, right, is called an event. Okay. But even before we talk about event, which will come up later, we want to talk about outcomes, right? Which in some way, you can think of it as elementary event, like the smallest event possible, okay? So here, right? When you conduct a random experiment, like, tossing a coin, tossing a dice, things like that, individual results are called the outcomes of the experiment, right? So it's very important, right? I mean, starting out, you see problems, one or two problems in the problem set, asking you to, right, list out the outcomes. Oh, sorry, right? Maybe so the sample space is basically the collection of all outcomes, right? So these are basically things you have to think about when you work on a probability of something. What are the possible outcomes? Right? What are the possible outcomes? And when you list that all out, that's the sample space. Why do you have to do so, right? Do you have to keep doing this for every problem? No, you don't, because that will be, right, very time consuming. But if you don't get into the habit, right, of at least thinking about this and then, have a clear picture of what they are in your mind, you skip over this step, if you will, then the later things you do will become hazy, right? So these are sort of like I said, building blocks, meaning they're kind of warming up things, but you get into the habit of thinking of them, right? So that when you think about them correctly, then, right, the steps we do later will become clear. So for example, right, when you toss a dice, right, what is the sample space? Well, right, of course, tossing a dice, the sample space will be 1, 2, etc. up to 6, right? So we call S. There are 6 outcomes, right, for the tossing of a dice, correct? Now, what about tossing 2 dice? Well, you might want to think about it a little bit, right? But when you toss 2 dice, right, what are the outcomes? The outcomes are, right, the results of the 2 dice, right? So, well, so it can be, so it's a pair of numbers, right? 1, 1, 1, 2, right? 1, 3, etc., right? And then I guess the last entry here will be 1, 6. And then you repeat with 2, 1, right? 2, 2, etc., up to 2, 6, right? And then this matrix continues until you get 6, 1, 6, 2, etc., up to 6 and 6, right? So that's the set of all possible outcomes when you roll 2 dice. Again, right, you don't have to list all these out like this, but you want to be able to think about them very quickly. And if you're not used to this, like the easiest thing to do is like work out these things, and then right you get used to thinking about them later on without writing them out. So right, of course, you'll see that the relevant questions is how many, right? How large is a sample space? How large is a sample space, right? Because intuitively, this has to do with the likelihood, right, of the outcomes in the sample space. We'll talk about that later. But for example, right here, there are 6 outcomes, right? And in here, there are how many outcomes? 6 squared, right? Equals to 36 outcomes, okay? And counting up this sample space and counting up the size of the events, we'll talk about that later, is the subject of combinatorics, right? Coming up in lecture 2 or 3, okay? So sample space of tossing a coin. Well, if you toss a coin, right, how many outcomes are there? 2 outcomes, right? Either head or tail. 2 coins, well, so it's a result of, right, the 2 coins. So you have head, 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 tail, tail, head, tail, tail. Okay. Any questions so far? So these are classical examples, right? I don't think they are anything too crazy, but as you see, right, the point is to be able to, right, at least visualize, right, the sample space of the random experiment you're dealing with. Okay. So, right, I guess the next interesting thing is about events, right? So if you look at your sample space here, right, there are about all outcomes, right? They are the set of all outcomes. But you might be interested in only certain kind of outcomes. For example, right, in this one right here, the tossing of 2 dice, you may want the set of outcomes such that the sum is 7. Okay, so clearly, right, that's a subset of this sample space. Here you might just want maybe, who knows, the even numbers, right? Here you may want maybe first head. Okay. So all these things I've written down, right, from the point of view of set, are just subset, right, of the sample space. Agree? Well, of course, right, I think you see a more intuitive meaning, right, about these things. There's something you're interested about, right? For example, when you roll 2 dice, you want to know the probability, right, of having the sum equals to 7. We'll get there, right? But to build up the language, right, to talk about these things, we have the outcomes, right? We have the size of the sample space, and then we talk about the event, all right, whose probability we're interested in. So that's what event is about, right? A subset of the sample space, a set of one or more outcomes. So here, right, we just want to kind of talk about the sort of like to make things consistent, right? So technically speaking, a set of one outcome rather is an event, right? For example, clearly we want, right, here, we want this to be an event too, right? Getting two heads. No reason why we don't want to include that as an event. So, right, an outcome is an event. Rather, right, a set of one outcome is an event. But an event, right, doesn't have to only consist of one outcome, right? An event can consist of many outcomes. So that's the only distinction we want to talk about right here. So outcome, you can think of it as like an elementary event, if you will, right? Meaning that there's no smaller, no sub-event within an outcome. Is that okay? All right. So now, again, right, I think we're just, the point is here, we're just building up the language, right? The vocabularies to talk about probability. But trust me, right? I mean, I guess a lot of you right now feel like these are so trivial, right? Why do we even bother? I'm not so sure. The reason is, right, I have had students on the exam, right? When talking about an event, they would write something like this. Instead of E, they would write P. And that's that. No, right? PE and E are not the same thing. I know, right? I mean, I don't know, right? To some of you, why bother? But PE, or probability of E, is a number, meaning it's the likelihood, right? It's the likelihood of E happening. While E itself is an event, these are not the same thing. You apply different operations to probability because probability is a number. You can add probabilities, for example, right? But events are set, so you can union intersection them. So, right, if you don't pay attention, you could do something like this. I think I've seen it. And again, right, this is, I strongly tell you, it's nonsense. You don't intersect two numbers. It means nothing. Again, right, I guess the students want to express the idea that is a probability of the intersection. Right, but I hope you appreciate the point that these are not the same thing. And that's why we have to go over this language, right? Because if you write something nonsense, if you will, then in principle, you don't get any point for writing that down because it means nothing to begin with. Is that okay? And again, right, I'm saying this because, you know, these days and age, right, ChatGPT takes over and you guys don't write a lot of things. But if you write something wrong or write something that's nonsense, then everything you write after that can be discounted without even, you know, question, right? So events and probabilities, we need to distinguish because of this kind of reason. Okay. All right. So I guess here, right? What is this example? And I think I've talked about, right, even here. Well, so here, right, you note that here, when I write even, is really a English word, right? But this must be or should be elaborated or extended, right? What do I mean by elaborate? By elaborate, I mean, well, tell me, right, what outcomes are in that event. Okay. Why do you care? Well, why do we care? So again, for example, it has to do with counting and it has to do with probabilities. So for example, right, I think there's not much to go here because everyone knows, right, that this is 2, 4, and 6, correct? So right here. E equals 2, 4, and 6, right? So that's how you write this event, okay? But, right, I mean, I think you start to see that it's non-trivial when you look at the event of getting a sum of 7. Why? Because again, right, how many? Eventually, that's the question we're asking. How many outcomes are in this event? Okay, so we need to elaborate only for that reason, that we need to know how many outcomes are in this event, right? And again, I guess we're kind of converging on the point of counting, right? We need to know the size of the events to do the probability, okay? We'll get there later. But this is why, like, for now, we're going through a very mechanical technique where we just list all outcomes. We're not doing anything sophisticated here, right? Sometimes listing is the best thing we can do, meaning that if there's no clear pattern, for us to do something a little bit more high level, then what we do is just list out, the outcomes in that event, right? To see what they are. So for example, right, when you toss 2 dice, then 1, 6, right? 6, 1, I guess, right? 2, 5, 5, 2, 4, 3, 3, 4, right? Are the events that have the sum equal to 7. Correct? But you see, right, the moment you write this down, then combined, right, with the sample size here being 36, right? And this event has size 6, then you can see intuitively, we haven't talked about this yet, right? I'm getting ahead of myself. But I guess I'm just want to kind of show you how this leads to probability. Because then, right, you see that the probability of getting a 7, getting a sum of 7, right, when you toss 2 dice will be 6 over 36. Or 1/6, right? Because, right, 6 is the size of the outcome, size of the event, and 36 is the size of sample space. Okay, and that's exactly why we need to do these things. List out this events and sample space. Any questions? All right. So now, exactly right. Now we talked about events. Event basically is a subset, right, of the sample space, or is a set. So as soon as we have a set, then we can do set combinations, right? Set operation. All right. And of course, right, set operation is meant to combine sets, right? So that's why we say it's combining events, right? The set theory people, right, of course, call it set. Us, we call events. But the correspondence is, there, right? So how can we combine sets? Well, you can have union, you can have intersection, and you can have complement, right? And in this class, right, or I guess in many classes maybe, you won't see, right, a problems that are given to you symbolically. You'll see a lot of word problems, okay? And the nature of word problems is that you have to translate, right, the English into symbolic language. So you need to understand the meaning, right, behind the symbols. So union, right, corresponds to or. Intersection corresponds to and, right? Complement corresponds to not. Okay. And I guess here maybe a Venn diagram, right? Demonstration might be helpful, but also you have seen it, right? So in a Venn diagram, right, the rectangle is meant to designate the sample space, the set of all outcomes. Circles are meant to designate, right, event, like so E and F, right? And so, right, of course, the part where the two circles have in common, right, is belongs to E and F, correct, together. So that's E intersect F. And by the way, right, the convention for this class is that we do not write down the symbol for intersection. If we write two sets next to each other, that's meant intersection, right? I mean, if you feel not used to it, and then in some cases we want to make things clear, then you can write down the whole intersection symbol. That's fine, right? But you know, sometimes to save space, right? A lot of places here in this class will combine the two letters together. That means intersection. That's it. That's the only abbreviation, right? Union is union, right? And so what's union? So if you pick anything, right, in any of these two circles, that's in E1 or E2, right? So that's why it's the whole thing, right? Everything here is the union, right? Sorry, not E union F, right? And if you limit yourself to, let's say, a picture of one set, right? This is S, right? This is E. Then anything outside of E is not in E, right? And so that's why it's E complement. Okay. So again, I think the Venn diagram here is not the first time you see it. We're just kind of, trying to make the connection and building things up slowly. But right, that's the reason behind the meaning of or, and complement. Okay. Any questions so far? All right. So the point, right, of this is that you can union intersection and complement event and still have an event, right? So these are ways you can combine events to get a newer event. Or as you see, right, the road is also backward, meaning you can have a complex event and you want to break it down as the union of smaller events, right? More simpler events. So you have a complex event E, okay? Complex, meaning hard to deal with. And you might want to break it down as the union of simpler events or something like that, who knows? But basically, right, the techniques doesn't have to always move forward, meaning that you union events to get events. You may want to also search for easier events somehow to combine to get to the more complex event that you're dealing with. All right, that's also a technique. Okay, so just to demonstrate, right? If E is the event that the first toss is head, and F, right, the event that the second toss is head, then again, right, to test your understanding here, what would E union F be? And we want to, right, list it out in terms of outcomes, right? We don't want to say it in English because if you say it in English, it's kind of trivial, right? First toss is head or second toss is head. Fine. What is it? What are the outcomes? If we union, right, the event that first toss is head and second toss is head, what do we get? We get head, 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 tail, and tail, head, correct? So the only thing we do not get is tail, tail, right? Because that's doesn't have first head or second head. Agreed? What about the intersection?
Both are heads, head.
Correct. What about the complement of the first one?
Tails.
That's not, again, right? Remember, may be clear in your mind, but it doesn't sound clear. What do we mean by tails?
Tails.
What are the outcomes? You mean
Not
telltale?
heads? Sure,
No,
telltale.
that's not the complement. Think about it.
Tailheads and telltale.
Correct. Right. See, that's why we need to be very precise about what we talk about. Tails alone is unclear. Telltale is incorrect. Right? It's tailhead and telltale. Do we agree? And then, of course, right, F complement will be telltale and headtail. Are we okay on this? So again, right, as some of you have participated, and that's great, right? Please do that. You demonstrate, right, exactly what's inherent in your thinking, which may seem very obvious to you, but is not precise or sometimes wrong, right? And this is why we need to list these things out. Because sure, right? I mean, casually, like, yeah, that's not head, so blah blah blah. But you're not. If you're not careful, you are either being not very clear, or you might get into a wrong idea. So that's why we have to list these things out, or we have to always have the means to list them out, so that we can be perfectly clear on who's right, who's wrong. I mean, when it comes to probability, at least, or events. Any question? All right. Okay. So here, right, this is a special slide that sort of says we won't really encounter this technical point very much in this class. It really belongs to a more advanced course. But basically, roughly speaking, it says that you can have an infinite union of events. Can be an event. I say can because this is where the technicality happens. Again, doesn't have to concern us so much, but the key word here is countable, which is a real analysis course, right? By the way, you do not have to have real analysis to be in this course, and it's not required, not relevant. But anything I want to say here in this course, I want to make sure it's precise and correct. So even though I'm expressing an idea that you don't need to know precisely, I will describe it precisely, right? So, but the point is that basically the previous slide, right, may give you the impression that you have to have finite, right, operation to have an event. That's not true, right? We can have infinite sample space with infinite combinations of event, and then still have event. Okay. So the example here is, right, roll a dice until you first see a 6. Now, when you think about it, right, again, reality, not reality, but your intuition, right, your empirical, your physical intuition may interfere, all right, with how we describe things in theory here. Why? Because when you think about physically rolling a dice until you see a 6, right? First see a 6, meaning, right, before that you don't see a 6, right? I hope that's clear. You probably will think of something along the line that, yeah, probably I just tossed about 10 times, I should see a 6, something along that line, right? But if you put away that bias and think about it carefully, then in theory, right, you can roll forever. I mean, again, forever is not the right word, but you can roll 1,000,000 times, right, and never see a 6, correct? That's possible. Again, right, it's possible, it's not improbable, right? It's a very tiny chance, I agree, right? Probably, right? You will never see it in your life that you roll a dice 1,000,000 times and never see a 6 because the chance is so tiny. But it's there, right? So basically what I'm trying to say is that when you roll a dice until you first see a 6, the sample space here is infinite. Okay? Because, right, you have no finite amount of outcome. You know, you don't have a definite upper bound on how many dice you can throw, right, before you see a 6, right? So the sample space is infinite here. And so, right, if you, among this sample space, right, if you let the event be that you roll an even number before you first see a 6, right? So what I'm trying to say here, what I'm trying to get to is just basically, right? Well, see that you can have a infinite event. I think that's really what I'm trying to get at for now, right? So, for example, basically, here's how I would describe the sample space, right? The sample space would be consisting of outcomes like this: 6, and so on, where X is not a 6. All right. So there you go, right? Basically, of course, right, we cannot do better than this. But what we're describing, right, is an idea that is a sequence, right, of letters ending, well, numbers rather, right, ending with a 6, where the leading numbers are not a 6. But of course, right, when we do this by itself, right, has many outcomes in it, right? Because this is not a 6, meaning, right, it's 1 to 5. Correct? So there are 25 outcomes in here. So on and so forth, right? So what we're doing here, like I said, is an abbreviation. But, right, that's the best we can do. Okay? And so among this, right, what is E? E, right, is the sequence with even length, correct? Okay, so far? So, right, the idea I'm describing here is that, basically, we can have infinite sample space and infinite event here. Why do I say E is a countable union of what outcomes? Well, trivially, right? E is a union of this and this. So union of this or this or this or this, right? But I mean, it's so trivial that I don't think it's worth going through here. Because here the idea is when I wrote this slide, I want to think of an outcome as an event. But when I look at it from this point of view, I think it's a bit trivial. So we can skip that for now, right? The point is, right, we can have infinite sample space and infinite event. Any question? All right. Yeah, right. So maybe let us move to the problem set a little bit. Oh, shoot. Okay, actually, I did not watch for the time. So it's almost 6:55, right? So let me give you the quiz for the day. So like I said, right, today's quiz will not be graded by precision. Just do something and submit by 7:05, as a warm-up, right? You get full credit if you submit, you'll get an excuse if you don't. But come Friday, right, you'll get the quiz will be enforced, and it'll be graded on precision. So the quiz today will be this, right? Describe the sample space of tossing 2 dice. All right, which, right, I have shown you before. And so, like I said, right, quizzes will be exactly from the materials I've shown you before, and you can access any materials you want. Okay, so I will turn off the audio and the video, right? You can take a break after you're done with the quiz, and we'll resume at 7:05. Okay. Any question before I turn off the audio and video for 10 minutes? Okay, so we'll resume at 7:05. Okay.
So we just have to describe the sample space and then take a picture and upload it to the assignment?
Correct.
Okay.
Exactly. That's your answer. I mean, so you write the answer to the quiz, however you want to do it. Upload the PDF file to the assignment. That's
Okay.
your answer to the quiz for the day.
Got
Does
it.
that make sense?
Yep.
For every day. let's continue. So any questions so far before we continue the lecture?
I had a quick question about the last example you gave.
The example, right? Okay, let me pull it up.
Yeah.
Yeah, go ahead.
So, are you able to find the probability of E for this?
Sure, but that's not, we're not there yet, right?
Okay.
But yeah, we can. And the point is, I mean, I can still give you some idea about it. The point is, you see that E, the probability of E here will be expressed through an infinite sum, right? Why? Because it has infinitely many outcomes. Each outcome, right, has a probability that is a number. So we're summing up, right, this probably outcome of these probabilities becoming an infinite sum. Probably what you're thinking about is a single number for E, which will be a analytical question. Can we find the exact answer for that infinite sum? But as far as the structure is concerned for us right now, E is an infinite event, therefore, or not therefore, but so it makes perfect sense that the probability of E will be at first expressed as a infinite sum, right? But there could be another clever way, right? Looking at E, and that's the whole point of probability. Like you can look at E, you can look at events in clever way, and you can get different an answer through a different way of looking at things. But yeah, so yes. So the short answer is yes, and most likely, if I look at for now, it will be an infinite sum. But yeah, we'll get there. Well, we're not there yet. Right now, we're just describing events. Okay.
Okay, thank you.
Sure. So where are we? Right. Yeah. So now let's move on to problem set. Oh wait, hold on. So I call this problem set, but I think, sorry, give me one moment real quick. I think I got the wrong materials. Let me see. Yeah, 1 second. All right. See if this is the right one. Yeah. All right. So, so we're moving on to problem set, right? And like I said, like you see this as a structure of this course that basically this class that basically we'll talk about the lecture, and then we'll look at a problem set where you'll see the problems that will be given to you, right, as a homework question, and the exams will be drawn from these questions. So you should be paying extra attention, right, to these problems. And so I'll show you the problem, right? Give you some time to, look at the problem, and then we'll discuss them, right? So I guess the problem will always have something to do with the lecture, right? They're meant to sort of like illustrate the lecture. So yeah. Okay. So the first question is about describing the sample space, right? And then basically there are two random experiments here, right? And then basically it's an exercise in describing what the sample space can be, right? So think about it and see. So for the first one, right, what would the sample space be? First of all, right, what are we describing?
what you'll get for the first and second marbles?
Excellent, right? So in that case, if you understand that, then what would be the sample space for the first one?
Or red, green, red, blue.
Correct, right? And then, of course, right, green, red, green, 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 blue, and then what? Blue, 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 red, blue, green, correct? So let's kind of see what we're having here, right? So first of all, right, this right here, this type of thing is called sample with replacement, right? Is in contrast with right here, where, right, this is called sample without replacement, right? And you can see, right, of course, the whole point is that it will change the sample space, right? It will change the sample space that we're dealing with. And it will change the size, and it will change the probabilities and things like that, right? Also, the way we list things out here, right? Clearly, for example, we have red, green, and green, red, for example, right? When we do it this way, what we're dealing with, or what the way we count it, is we implicitly say that order matters. Is that okay? Because, right, we say red, green is one outcome and green, red is another outcome. If we decide to combine these together as one event, then order does not matter, is what we're doing. But notice, right, that here we should not do that in that case. In this case, right? Why? Because green, red, and green, red, and red, green, red, and red, green, right, are two separate outcomes who, right, you can intuitively feel likelihood is the same as red, red. So if you lump red, green, and green, red together as one outcome, then the outcome of that lumped, the probability, let's say the likelihood of that lumped outcome will not be the same as the one red, red. You understand? So the way we list things out here, all outcomes have the same probability. So again, getting ahead of myself, but the way we list things out here, all outcomes are equally likely, right? So these are terms that will matter later on, but I want to introduce them right now, right? Sample with replacement or without replacement, order matters or order does not matter, and outcomes being equally likely or outcomes not being equally likely, okay? So here is natural, okay? And that's probably is a loaded word, but it's natural that we have order matters so that the outcomes are equally likely. Any question so far? So for the second marble, right? Sorry, it's the second sample space, right? Without replacement, what will happen? Without replacement, right? Then the difference will be that we cannot have repeat. Agree? Because once you drawn it, right, it's gone. So the only, right, possibility is either red, green, red, blue, or green, blue. And notice, right, of course, I could do also, let's call it S2 prime, which is red, green, green, red, red, blue, blue, red, green, blue, blue, green. I could do this too. But what's the difference? The difference is here, order matters. Here, order not matters, or does not matters. You know, I'm lazy to write the word does. Do we understand? And why can I do this here with S2? while I don't want to do that with S1. You see the point? The point is that, right, if I lump this together, they're still equally likely. So either way is fine here. But if I lump red, green, green, red together, right, it's not the same likelihood as red, red. So I would do much better to leave them all separately. Do you understand? So again, right, getting ahead of myself, because the point here is not about probability, but just about describing sample space. But I guess, right, I'm getting to that subtle point where how you list the sample space affects how you can compute probabilities. So you want to be very careful about these kind of things. Any question? Okay, so here. So here's the official answer, where I guess, right, for consistency, you see that I keep order matters in both cases. But in the answer I give you here, I also tell you about the possibility of making it order not matters. These are okay for the second one. But the official answer, I'll just make it easy, make order matters in both cases. Are we good? Any question? All right, so let's see the second question. So, right, I guess we saw this before a little bit in the lecture, but this is a problem. So the point with number 2 here is how you express the answer, right? As I kind of give you the hint about. But this is dealing with an infinite sample space, right? Where you have to describe certain kind of outcomes and certain kind of events. Oh, sorry, there's a typo here. Here, En is the event that n rows, right, are necessary to complete the experiment. Let me fix that. Okay. All right, any idea, any question about this problem before I show you the solution and discuss it? All right. So, right, so first of all, notice, right, the sample space is a collection of all sequence of length n that end in a 6, right, but does not contain a 6 in any previous letters, right? So as I show you, it's 6, x6, xx6, etc., right? So En, right, is basically, right, the sequence of length n, right, that ends in a 6. All right. And here is an aside. You can ignore this for now. But basically, right, what I'm trying to say here is that the probability, right, of E1, which is getting a 6 on the first row, clearly is not the same as the probability of getting a 6 on the second row, right? And of course, it's not the same as probability of getting a 6 on the third row, right? Of course, what this means is a 6 on the second row and not a 6 on the first row. It's a 6 on the third row and not a 6 on the first 2 rows. Do you understand? So here I say they are not equally likely. Again, just as an aside, because when we say equally likely, you'll see that later on. The word equally likely really apply to outcomes, not event. So I'm just kind of cautioning you here to distinguish between events and outcomes. But we use the word equally likely a lot later on, you see. But when we say equally likely, we apply to outcomes and not events. So here, right, this really is not super necessary, but I just want to point it out in connection to outcomes. Okay. Now on to the last part. What is the union of En complement? Notice, right, there's a complement here. So you want to kind of understand what that means, right? So the union of En, right, is basically getting, right, a 6 at some point. Agree? If you just look at the union of En, then even though it looks scary, it really means, right, that taking all the outcomes, right? Because this sample space, this event is rolling, right, until you get a 6. And then En is a subset of that has length n. So if you collect all of that, well, you're talking about everything then, right? So this really is just a fancy way to talk about the sample space. And so, of course, if you complement, sorry, omega here, right, is, I guess, my old style to write S, which is a sample space. So S complement is nothing, the empty event. Any question about this answer or this question, this problem? All right. So I guess the next one deals with probability. So we'll get there when we cover the theory for it. But right, the first two questions are meant to kind of illustrate to you about sample space and outcomes and events. So any question about this? All right. So, all right, I guess before we talk about probability, we have one last slide to talk about. Basically, right, when you combine events, basically there's some rules that you can use to speed things up. But basically, right, the laws here are laws of combining set. Okay. And we'll just talk about the basic laws here that if you take any set theory or you just learn about sets, you will know them. So these are called commutative law or basically symmetry, right? When you take intersection or when you take union, you can do it in any order you want. Associativity, right? When you take intersection or when you take union, you can do it in some order first, or you can do some group of two first and then do the last one later. In which case, right, they all agree. So basically, right, how you combine intersections and unions don't matter, don't affect the final result. Distributive law, right? Distributive, not distributive, right? Distributive law. So here, right, when you have intersection and then you union, you can distribute the union inside the intersection, right? When you have union and then you intersect, you can distribute the intersection inside the union. All right. So this is very helpful in some circumstances where, right, you have to deal with this expression and you want to write in that expression, for example. Last but not least, De Morgan's law. The complement of the union is the intersection of complement. Okay. And I guess maybe, I'm not sure if a Venn diagram can try to demonstrate this, right? But if you have the union, right, which is right here of two sets, and you take the complement of it, that means you're looking at this part right here, right, outside. This is the union of E union F complement. Right? On the other hand, right, if you take the complement of the first set, then you look at this part right here, right? And you look at the complement of the second set, you look at this part right here. And so what do they have in common? What they have in common exactly is the parts that outside both sets. Right? I guess I'm not sure. Let me try more color. See if that helps. Right? If you look at the complement of the first set, right, then you have right that, right? If you look at a complement of the second set, you have these. Sorry, the color is not, but right, the part where they both have in common is the part outside both sets, right? Which is exactly this two. Okay, but it works in general, right? It works with more than two sets. All right. So again, right, be very careful here because I don't know, right? I mean, these things are sort of like maybe basics, but I have students who on my exam write the Morgan's law, I don't know, like this. Okay. Again, maybe I say this too many times now. For you, maybe this and this don't seem any different, but for I guess the ones who the people who care, they're not the same, right? Why so? This and that are not the same because the way you write this reads as you take the complement first and then you union it up, right? Here you union first and then take the complement. The order here is very different. So here you're basically saying something nonsensical again, because you're saying you take the union of some set is the same as you take intersection of the same one, because the complement here doesn't mean anything, right? So symbolically, I guess, right, these are straightforward maybe, or I don't know, maybe intuitively they're straightforward. But if you just catch the symbols and try to write down something that you think is correct, you might end up with something very far from the truth. So try to understand the ideas very clearly, right? And then write down the symbols for it. Please don't just memorize the symbols. You will get it wrong. Right. Any question here about any of these laws? Okay. So now moving on, right? We'll see at least some of these again later. But now we move to probability, right? So to repeat, right, we have outcomes, and then we have events, and then we have sample space, right? But so far we have not talked about probability, and now we will, right? So probability, what is it? Is a way to assign numerical value to event. Meaning you have an event E, you will assign, right, a number to E that's supposed to represent its likelihood, right? Of course, right, the higher PE, I guess we all intuitively feel this, the more likely, right, we think E will happen. That's, you know, the interpretation. All right. But clearly, right, you cannot just go in and they say, well, you know, let me assign, I don't know, 0.5 for E, and then for E complement, let me assign 0.4. All right. If you assign PE, sorry, maybe let me be a little bit more. So when you say PE is 0.5 and PE complement, let's say is 0.4, what you have done here is a contradiction or a inconsistency. All right. So basically, so sorry, I should not use the word contradiction. So basically, you have violated the accidental probabilities. So what I'm trying to say, right, is that you cannot just go in and say, I will assign some numbers arbitrarily, right, to PE. They have to follow certain kind of laws, and that's called the accidental probability. All right, and it's the accidental probabilities that it give us, right, the way to operate with probabilities and what you're here to learn about. So what are the axioms? Again, right, keep in mind that the axioms are reasonable, meaning they're supposed to capture what we feel, right, how we feel probability should work. Okay, so first of all, what? The empty event should have probability 0, right? Because the probability of, so by the way, right, the empty event doesn't mean nothing, but the empty event kind of represents the impossible event. Okay, for example, right, you think about it. For example, when you intersect, right, head tail with tail tail, let's say, right? By the way, right, be very careful here. Head tail intersect with tail is not second one tail. Do we understand? Because again, right, this is where if you just case symbol, then you're like, yeah, when you intersect head tail with tail, don't you get a second tail? No, because when we mean head tail is a set with only one outcome, that outcome is head tail. When we mean tail is a set of one outcome, that's tail. Do they have anything in common? Head tail and tail? The answer is no, right? So head tail intersect with tail is not second tail. All right, please be very careful. But the intersection is empty, right? So the probability of this is 0, right? Again, I'm probably demonstrating something very trivial here, but might be a bit nuanced in terms of symbols. But right, when you think about it, why is it 0? Well, because you cannot draw 2 coins and get head tail and tail at the same time. Agree? It's impossible. You must have either head tail or something else. You can have head tail and tail at the same time. Correct? Of course, I'm doing something very trivial. There are others, examples that are a bit less trivial. But I'm just describing, the idea that empty set means impossibility. Okay. And so the probability of the whole sample space is 1 because that's just basically, right, means something happens, something like that. So that's why, right, the probability of something happens must be 1, right? Because in an event, something must happen. So basically, yeah. But other than that, right, an event must have probability between 0 and 1. Notice, right, equalities are allowed. So it's a bit subtle, and you'll see. But you don't have to be the sample space to have probability 1, and you don't have to be the empty event to have probability 0. You see this, for example, right, when we deal with continuous random variable, where, right, I mean, I'll give you an intuitive thing, but if you drop a needle, right, let's say on the interval 0 to 1, uniformly, all right, if you try to drop a needle, right, a very super thin needle, like atomic level or even subatomic level, then you drop a needle on 0, 1 and you hit the value 0.5 precisely. So the probability of hitting a 0.5 will be 0 when you drop a needle uniformly on the interval 0, 1. Okay. Why so? It's because there's so many events, right, between 0 and 1, so many outcomes, uncountably many. That's why the probability of hitting a value precisely here is 0. But it's not an empty, right, event, because 0.5 is an outcome, right? But the probability of that outcome is 0. So that's a weird thing about continuous random variable we'll talk about later on. But right, I'm just kind of trying to tell you that an event doesn't have to have probability, doesn't have to be the whole sample space or an empty event to take on those niche value of 0 to 1. All right. So here's just a kind of terminology, okay? So two events, when we say they're mutually exclusive, that means they have nothing in common, right? So the Venn diagram is this, right? They have nothing in common. So this is mutually exclusive. All right. And so for events that are mutually exclusive, then the axiom of probabilities say that, right? The probability of the union is the sum of the probabilities. Okay. So if events have nothing in common, then probability of this or that is probability of this plus probability of that. Okay. So you just sum it up. But as anything within probability, right, it's very easy to make a mistake here when you ignore the condition. Because in general, right, the probability of the union is not the sum of the probability. This is the number one mistake, I guess, let's say mistake 101, right? The probability of the union is not the sum of the probability in general, okay? Only true if events are mutually exclusive. So we'll talk about the general law here in the next slide, right? It's called the inclusion-exclusion formula, a very important law that we'll use throughout the course. But I'll pause here to see if there's any question about the axiom of probabilities. Okay. So right here, right, is the inclusion-exclusion formula. The probability of the union is a sum of the probability minus the probability of the intersection. Okay. And you can see, right, this is consistent with, let's say, if, right, EF is empty, right, if E and EF are mutually exclusive, then clearly, right, by the axiom of probability, PEF is 0, right? So the law of inclusion-exclusion formula will say P of E union F is PE plus PF minus, right, PF, which is 0, right? Because, you know, it's empty. So that's, of course, equal to PE plus PF, right? So in this sense, right, the inclusion-exclusion formula is more general, right, than the special case here, right? But it's consistent with that special case. Okay. Any question about the inclusion-exclusion formula at the two set level? All right. But I guess, right, let's backtrack and look at the other, I guess, simpler things, right? So the first one actually is a very, very simple consequence, but it's important, especially, right, to go with De Morgan's law, right? The probability of the complement is 1 minus the probability of the set. So that's why, right, when I said, you know, when you assign 0.5 and 0.4 here, right, is a violation of the axiom probabilities because, right, they have to sum up to 1. Okay. So let us be a little bit pedantic here, right? can we explain, right, using the axiom of probabilities, why this is true? Again, right, I mean, for some of you, you may not be used to this. You might think this is obvious. That's okay. I mean, at this level, it doesn't really matter. But the point here is that it cannot be obvious in the sense that it's intuitively true. Because the point of view we're taking, right, is that there are laws right here that we accept, meaning they're axioms, so we don't question them, okay? But anything after that must be somehow derivable from the axioms, okay? So, like I said, it doesn't hurt if you accept this as like some sort of like obvious truth, because we're not doing a proof class here, but I want to at least show, right, you that it's derived, right, from the axioms. So do you see how? Okay, so here's how it's derived from the axiom. So first, right, note that E union E complement is the sample space. Agree? Therefore, P of E union E complement is equal to P of S. But by the axiom of probability, P of S is 1. Also, right, E and E complement, of course, are mutually exclusive. Therefore, by the axiom of probability again, this is P of E plus P of E complement, from which we have this. All right. Any question? So the next one, right, is also something rather obvious to rather intuitive, right? If an event is contained in another event, then its probability cannot be more than the other one, right? By the way, right, this has some meaning. This is set theory, right? A set is a subset of another set. But in terms of logic or in terms of meaning, this means E implies F, or right here. Okay. If a subset is contained in another set, right? Then if E is a subset of F, then a member of E, right, being in E implies that you're also in F. That's why E implies F. Okay. So in terms of logic, if an event implies another event, right? If you roll a 2, that means that implies that you also roll an even number in terms of rolling a dice. Therefore, the probability of getting a 2 cannot be more, right? Or it's always less than or equal to the probability of rolling an even number when you roll dice. Okay, as an example. So now, right, the question is why? Can we show this from the axiom of probabilities? Similar to this. Can anyone see how it's done? Okay, so here, right, Venn diagram might be a bit helpful just to write down the symbols. So you have E, right? And then F is a bigger event, right, that contains E. All right. So in this sense, you can write F as a come as a union of two sets. The first one is E, of course. And the second, right, is the part that is in F, but not in E. So how do we write that? In F, but not in E. So it's FE complement. Right? So therefore, P of F is equal to P of E union FE complement. On the other hand, right, it should also be clear that E and FE complement are mutually exclusive. Why? Well, why is because, right, this is E and this is inside E complement. So they cannot have anything in common. But, right, by accidental probability, so let me go down here, okay? By accidental probability, right, P of F then is going to be equal to P of E plus, right, P of FE complement, because these guys are mutually exclusive. And now, right, we will use the last, this piece of accidental probability that says that the probability has always to be non-negative, which means this guy right here, right, whatever it is non-negative. But if it's non-negative, then clearly this is bigger than or equal to this. So that's how we derive this from the axioms. Any question? All right. So here, right, is the demonstration, right, of the inclusion-exclusion principle that we just talked about here. Right. So you see, right, basically, if you have two sets, right, then if you take the size of both sets by summing the size of the first set and then the size of the second set, what you ended up doing, right, is you add the part they have in common twice, or double counting. So that's why you have to subtract it once to balance out the sign. So that's the picture, right, demonstration of the inclusion-exclusion formula for two sets. Okay, any question? So there's general inclusion-exclusion formula, right? For three sets, and then for n sets. Okay, these are very important again, very, very important. But I'm just showing you what's coming up so that you don't think that this is the end of the story. But let us do a few problems, right, for the last 5 minutes, and then we'll go into these, if not today, then next lecture. Okay? Any question before we continue with the problem? Problems. All right. Okay. So here's number 3. And let's take some time here, right? I want you to think about it and then propose the answer here if you want. The point of number 3 here is to kind of train you on, the language, right? Because here, right, the question is in English and you just have to translate into set language as we talked about and then calculate out the numbers. So, right, look at it, try it out a little bit if you want, and then we'll talk about the answer. So pay attention, right? Here, A and B are mutually exclusive. So again, right, what that means is AB is empty. So A, right, what probability are we talking about? In terms of set? A is the union, right? And because A and B are mutually exclusive, it's a sum. Right? Well, B. What expression is B about? So A occurs,
and
right?
B,
Yeah, sorry, sorry.
A
Go ahead.
and B complement.
A intersect B complement, very good. Very good. Now, so what's the answer to this? What's probably A and B complement? Well, Venn diagram might be helpful, or right, you should try to draw a picture. Doesn't hurt, right? This is a picture for A, right? B mutually exclusive. So what does A and B complement look like to you?
Just A.
Correct. Okay, what about C? A and B both occur. What is that? That's AB, right? And the answer here is
0.
correct. Okay, any question here? All right, so I think, right, it's almost 7:55, so we'll stop here today. This problem set, right, will be posted, if not later on tonight, then tomorrow as homework one, okay? Lecture slides will be posted, but the problem set will be posted without solutions, right? And you have until Friday, right, to turn it in. But of course, we'll go over them in class as well. Okay, so look out for those things. If you have any questions, send me an email or ask me now. If not, have a good night, and I'll see you on Wednesday. Okay.
Bye bye. Have a good one.
You too.